Hello! In my last video I told you about my quest to seek the knowledge to build an AND gate. I discussed how I was going to know that I found a valid solution and how to avoid some of the illusory false copies that are around. I also promised a series of videos about that journey, which led me to explore different solutions. What I'm about to show you is not the first solution I came up with, and it's also an unlikely first stop for anyone following my path today. Exactly because of that, I find it worth telling about. While researching for my journey, I found an ancient tome of wisdom that described several possible roads that could lead to my goal. One of them involved diodes. I knew some of the popular lore about diodes, but I had never dealt with them directly, and I wasn't aware that it was possible to do logic gates with them. That only means that exploring this avenue would definitely result in me learning something, even if I wasn't successful. I will share with you all of my deep knowledge that I had before starting this. These are some diodes. There are many different kinds, and I know some of the differences are how much voltage or current they can handle. But there are possibly other aspects of change I knew nothing about. They are represented by this symbol, looking like an arrow. And the arrow shape is important because they are not symmetrical, and putting them this way will work very different than putting them this other way. So the color bar, or in this case like a silver bar at the end, corresponds to the pointy side of the arrow. And the most important of all, a diode allows current to flow only in the direction of the arrow. Let's test this directional property with a simple example. I have here a simple circuit with a LED and a resistor. This wire can bring power to the LED. If I remove the wire and put the diode instead, the circuit keeps working because the arrow points in the direction of the current. But if I flip it backwards, current stops flowing through the diode and the LED is no longer on. So far, my intuition seems to be good enough. This makes the diode quite different from the resistor or the wire, which can be flipped over with no effect on the circuit, and more similar to the power supply and the LED, which you can't flip over. In fact, the LED is very similar because it is a diode. The D in LED stands for diode. Now you know why this episode is about diodes and diodes. With this knowledge, I still have no idea how a diode could help me build a logic circuit. Our previous wrong AND gate using push buttons at least produces the right result, so I was looking for components that act kind of like switches, and a diode doesn't seem to be that. Until I saw some of the diagrams, and the penny dropped. The diode is not exactly a switch, but still has two different modes. In one of them, current flows, and in the other one, it doesn't. It's just that you control it with the same voltage that you are using for sending power, so it's a bit tricky. But let's try to do something with this. Let's build a circuit where this green wire over here is an input, and after the input I have a diode pointing that way, to the left. Notice that the diode is pointing towards the input, which seems counterintuitive, but at this point it's important to notice that I don't care about the flow of the current, but how can I control voltage levels across the diode? So let's put the positive side of the diode, it's usually called the anode, to 5 volts. If I do this and I connect this input to a high level, then there will be no current flowing because both sides of the diode are actually the same voltage, both are 5 volts. If I connect this to a low level, and I won't do it, current will actually flow directly from 5 volts to 0 volts, shorting this circuit and sending lots of current through this diode and probably burning it up. So what I need to do is take this and add a small 220 ohm resistor here to protect the diode. So now current will flow only on a low input and it will stop flowing on a high input. So this kind of acts like a switch. Some of it is backwards in the sense of current flow and what opens and what closes it. So if we call this junction over here the output of this circuit, I can pop a LED there. So let's mark the output as the small blue wire over here and tie this output to a LED that should be connected to ground at the end. When the input is high, the diode is closed, so current flows through the resistor into the LED and to the ground. If my input is low, current flows through the diode directly into the ground rather than going through the LED. This is not a really interesting gate. I could have hooked the input directly to the LED, but there is something interesting going on here. The input is controlling the current which is moving elsewhere, which is kind of what we were looking for. Let me make a little change here. I can add a second diode here and tie a second input to this circuit. Now let's connect these two diodes together and let's call this the output. Now if any of these two diodes is open, current will go from the top towards one or both of the inputs into the ground and will not get towards the output, and in particular towards, for example, let's say this LED over here. The only way to get current to the LED is if both diodes are closed, and to close the diodes both inputs need to be high, which is exactly what we were hunting for. Let's demo this. So both inputs are low, and one is low, the other high. One is high, the other low. In all of those cases, the LED is off. But when both are high, and notice that this has this weird behavior when this is floating, but doesn't matter. When both are high, I get the result I wanted. The output is high. There it is. This behaves like the AND function. That was our rule number one. But we've been disillusioned before. So how do we know if this is a proper gate or another more subtle mirage than before? We will need to verify this. Let's start by hooking these nice buttons I have here to make things easier. That way I will be able to control my presumed AND gate with these clicky things. So let me show you. Okay, so there's something weird going on. So perhaps you can see that my green LEDs are actually flickering a little bit. And that's actually because, well, as we mentioned before, this gate is a bit strange because the inputs are actually sending current. So the current is lighting my LEDs. So my LEDs won't help much. Let me remove them. Now I still have two buttons and it still doesn't work. So you can see if I press the button, the glow increases a tiny bit, but it's still on in this case where it should be off. There's something very wrong going on here. What I'm getting is not what I expected, so follow me along as I debug this. When I get an unexpected output out of a system, the cause for it usually falls into three categories. The first one, the system doesn't do what I actually expect. The second one, the system actually works, but I'm feeding the wrong data. And the third possible cause is that the system is actually working, but my expectations are wrong. That is, I miscalculated the output that I should be getting. The AND function is simple enough to feel that I'm likely to know the right result, so I'll discard number 3 now. And I usually prefer to check number 2 before number 1, especially if it's easy. So let's do some measurement. If you follow other channels in YouTube where they talk about electronics, you know that this is time where they pull out an expensive looking oscilloscope. So here's my 2 coffee worth multimeter, and I've set it up to measure volts. let's hook the ground to this conveniently placed probe over there and make some measurements. So this is ground around 0. This should be 5 volts, so it's fine. My power source seems to be working. Let's test what my buttons are outputting. If I press it and I measure there, I'll get around 5 volts, which is what I wanted. That looks good. If I release it, I get 215. That doesn't seem right. I would expect to get a 0. So my low is not very low, and I think it's the button circuitry. Let's make this even simpler. Let's go back to the single diode. So I'll remove this, I'll remove this, and now we have only one button. And if I measure here, I'm still getting 2.2 for the unpressed button. As you can see, we still have the same issue. That means that my low values for the button are pretty bad, 2.2 volts rather than 0 volts. And if I put the gate into a real 0 volts, it actually works fine. And the button by itself actually did work. When we have the green LEDs, it was working. And actually, if I unplug this, let's measure. Now I have 0 volts here, and close to 5 volts when it's pressed. It's a bit wobbly, so and the number changes, but it's still pretty decent. So both parts work by themselves, but they don't work together. Let's try to understand why. There is a combination of factors here causing problems. Let's draw a diagram for this. In the push button, I want to select between 5 volts and 0 volts. And I have this wire going to 5 volts directly, so I get 5 volts when the button is pushed, and that seems to work. But when I release the button, I don't want this end to be disconnected, but close to 0 volts. And I cannot put a wire to 0 volt directly because that will short my power supply when I push the button. So I added this button resistor, and the amount didn't matter much at this point, so I chose a arbitrarily 1000 ohm. The more the better here, because this is just to prevent a short, and small resistances waste more power. I can actually ignore this left side because my problem happens when the button is released. In this case, all of this is disconnected. Now let's link to our gate, which is the diode, and this resistor here going up to my 5 volts rail. So this gate resistor is, again, to prevent the short if I connect the input directly to 0 volts, which is something that should be allowed. I used a 220 ohms because this also limits the current to the, for example, the output LED. And I would like the LED to be quite bright. And in general, I want my gate to have a good current output, which will allow me to connect it to more stuff. So this is the problem circuit. It only has 3 components. Current comes from the 5 volts through this resistor into the diode, and through this resistor into the ground. Luckily, I did read some basic theory, and I know that if my circuit is fully sequential, the current flowing through each one of these components is the same. And I also know Ohm's law, that describes the voltage drop at a resistance based on its value, and the current, which is the same for both resistors. Even without knowing a lot about the diode here in the middle, I know that this resistor is currently about 5 times bigger than this other one over here, and the currents are the same. That means that the voltage drop in this resistor is going to be about 5 times the drop in this resistor. Without doing the exact math, this is telling me that the distance between this voltage here and this point over here is going to be big, and the distance between this point and this point over here, 5 volts, is going to be small. which means that this voltage will be closer to 5 volts than 0 volt, which is the problem I'm having. My low value here is pretty big, and this voltage is too high when the button is released, which is the situation we are considering. How do we solve this then? We could fiddle with the resistor values, and that would mitigate the issue a bit, but the core problem would still be there. What we have found is a limitation of our gate. It doesn't play nicely with a pull down to low input. It still works fine with clean 0 volts or 5 volts inputs when I plug them directly to the rail. What we can do instead is change our button setup. What we need is not to use a pull down resistor. For this kind of push button, I would have to reverse the logic and have a pull up resistor, which means that the button will be high when released and low when pressed. That's the opposite than the usual, unless I change this for a normally closed button, but I don't have any of those. Still, the input values are fine, and we can put back the LEDs to show what's going on. Let's make this change, rebuild the gate, and test. So that's connected to 5V. Let's add some LEDs. And LEDs should go to ground. Okay, let's power this up. Now it seems we're getting the right result. Output is high only when both inputs are high, which is both buttons are released now. And if I press any of them, or both, the inputs go low and the output goes low too. If we measure the inputs, now they should be cleaner. So that's 0 volts, and that's still not 5 volts, and that's because the LED is kind of interfering with this result. So I'll have to take them away still. Let me do that. So now we have 5 volts when this is released and 0 volts when this is pressed, which is what we want. And the gate still seems to work the proper way. So why doesn't this pull-up resistor have a voltage drop? And that's because now my path through the resistors, which is going through the resistor into the diode and back in the resistor, is going from 5 volts to 5 volts. So there's no voltage difference to drop. So let's measure the output point, the result of the gate. For the low, we can see around 0.8, 0.9 volts. Not exactly 0, but good enough. And for the high, I have again 3.8 volts. So let's do it without the LED to avoid interference. And now we can see that we get clean 5 volts. And still we get 0.8 volts without any of the LEDs. So that's not exactly 0, but it's good enough. This is looking really promising. We just need our final test. Can these gates be composed? Let's extend our current circuit into this. So we will need another 2 diodes and essentially the same setup. We need an extra input here, which I will bring high, so it's easy to test. And let's test. So if I press this, or both, I get a low, which is what I expected. And if this second AND gate has a low input, the result will be low no matter what I do here. So that looks really good. Are we really sure that this composes well? I bought 10 diodes just for this video. I just only use 4, so I'm not running out yet. Let's build a third one, just in case. Okay, so I rebuilt this and plugged this to everything to 0. Well, almost everything. So let's power this up. And it seems to be off. So unless I set everything to 5 volts, the LED should be off. But however, you probably can see that it's glowing a little bit. So there's something off going on here. And of course I put everything in 5 volts. The LED lights up brightly. But in other cases, it kind of has this flicker, but it doesn't go fully away. So let's see what's going on here again. And let's measure some important points. So at this point, I'm getting 0.2 volts. That should be 0, but that's probably my breadboard going a bit flaky. Yeah, that's a bit better. So that's 0.06 volts. And after the first gate, I have 0.8. And after the second gate, I got 1.7. So roughly double the one before. And right here, I have 2.4. And if I remove this, yes, I get almost 2.5 volts after the third gate, which is kind of in the middle point between low and high. It's quite indeterminate. There's something going on here. And something I want to show you is this problem shows a bit more, and that's a bit funny. If I just change the color of the LED, if I put a red one, you can see it's actually a bit brighter, and the voltage here goes down to 2.32. Well, let me remove this resistor to avoid confusing stuff. So now you can hear that the red LED goes really bright, and the blue one is kind of a bit better in this case. Roughly, depends on how much I fiddle with the wires. My signal is degrading. Why so? My initial assumption was wrong. Diodes, the light emitting ones and the others, are not just an on-off switch based on direction of current. They require a bit of voltage to go across, even towards the arrow, and they spend that voltage. So if a diode is conducting, there will be a voltage difference across the ends. This drop depends a bit on the amount of current and on the ambient temperature, but the main factor is the material of the diode. My regular diodes are silicon, which usually drops about 0.7 volts, and each color of LEDs has a different chemistry. My red LEDs are gallium arsenide phosphide, which have a typical drop of 1.8 volts. And my blue LEDs are gallium nitride, which has a drop of 2.4 volts. By the way, Veritasium made a great documentary about the discovery of blue LED chemistry that I'll link in the description if you want to learn more. But going back to our problem, these black diodes have a total drop of 2.4 volts, which means the voltage is just enough to turn the blue LED. But this point is almost off because it's 2.42. But this voltage is perfectly fine to turn on the red one. When I plug in the LED, the voltage at this point falls, and this 2.0 is actually the voltage drop for my red LED.
You can find these values in the datasheet for the LED, although you'll see that they change a little bit over temperature. So the question is, can we fix this? There's no solution just with diodes to prevent this signal degradation. You could use other components like transistors to fix it, but we'll see soon that the components you'd use can be used to build gates on their own. So an error on the signal on itself wouldn't be a big deal, but the problem is that the errors are being compounded. That means that when we chain gates together, the errors will accumulate until we don't know what's a high or what's a low. So diode gates kind of work in some situations, but they have a rough time complying rule number 1 and rule number 2 at the same time. You can also use diodes to build OR gates with forward diodes, which will have a similar issue, dropping voltage for the highs rather than increasing the lows. And they are also quite picky on the inputs. If you combine them with other inputs with pull-down resistors, like the diode OR gate with the diode AND gate, you end up with the intermediate voltages that we had when we built the initial button. The final problem is you cannot build NOT gates with diodes. In the end, this was not the gate we were looking for, but it's my closest approximation so far. This gate, called Diode-Resistor Logic, has been good enough in practice to build some real computers or parts of some real computers in the 50s. Given that they have some issues, it's not something you put to flame a nuclear missile, except that this is exactly what some of these diode logic computers did. The Minuteman 1 intercontinental ballistic missile has a lot of these diode gates with a few transistors, more expensive at the time, to fix signal degradation issues. In our next video, we will start exploring the most popular destination to hunt for AND gates, the transistor.